As we know, our main Bodin components are iron ore, sinter, pellet, coke, and fluxes. Now, cooking is in blast furnace is pretty unique. So we don't have the luxury of perfect raw material. We dealt with a high alumina ore, particularly, especially in our context. That is a challenge for us. And these alumina ore that makes like thick and sticky and high ash coke that can choke the gas flow. Therefore, our three key objective in designing any burden are that is first to shape the cohesive zone for maximum productivity, second keep gas flowing smoothly to avoid hanging, and third is to engineer a slag that's fluid enough. So remember, a poor burden structure leads to low production, high fuel rate, and a very unhappy furnace. So before you touch a single raw material, you must know your targets. So look at these three pillars. First, the company asks for a daily TPD and productivity. Higher productivity means pushing more air and oxygen. Second, the steel shop downstream want hot metal with specific silicon and sulfur level for steel making. Third, to achieve those we must engineer the slag. So we look at the B2 ratio, a certain amount of magnesia to fluidize the slag, especially important with our high alumina ore. And we always aim for low slag volume, ideally under 300 kg per ton hot metal. Why? Because every kg of slag needs heat to melt and causes erosion of the furnace also. So your burden calculation is the tool for the delivering three targets. So let's get practical. How do we actually do the maths? So here is a 5-step recipe. First, you lock in your TPD and productivity targets. Second, you decide the final hot metal and slag chemistry. And third, you perform a mass balance. So calculating exactly how much iron, silica and lime is entering, this tells you how much flux to add. Fourth, you finalize the aggregate burden mix. Is it 70% sinter or 20% pellet or 10% lump? So these mix determine your gas flow and reducibility. Fifth, you convert everything to plant data, the kg per ton of hot metal. So this is your daily charging sheet. This recipe ensure your furnace get exactly what is needed to hit the KPI. Now for the art of burden design. This is the magic inside the furnace. The cohesive zone is a layer where the burden softens and melts. If your burden distribution is strong, the cohesive zone looks like an M or V forcing air to channel only in the center, choking the furnace. So your job is to design a wide, flat cohesive zone. How? By controlling the distribution of ores versus coke, improving pellet quality, and maintaining the right ore by coke ratio. A flatter zone allows the gas to flow uniformly across the diameter, resulting in higher productivity and lower coke rate. Manage the cohesive zone and you manage the furnace. So let's look at the champion, the blast furnace at the axe. This is not theory, this is a real Indian iron making. They achieved an average monthly productivity of around 2.77 to 2.8 TPD per meter cube and a peak of 3.17 TPD per meter cube. So how did they do it? By using a high center burden mix to improve reducibility and aggressively injecting 150 more than 150 kg per ton hot metal of pulverized coal. So this is the perfect example of formula we learned. A flat cohesive zone plus high reducibility plus proper slag chemistry is equal to massive productivity. So this proves that despite our challenging high alumina high ash raw material, world-class productivity is achievable with scientific burden design. Your target is to design your daily burden to match this level of performance.